Welcome to the Ashby Village Science and Ideas Group. I'm Joe Evinger, and I coordinate this group's events with the help of our co-host and tech expert, Hilary Naylor. All of our members here have varied educational and work backgrounds, but we all share one common interest in science and new ideas. We have over 70 members in our group and another 100 on our guest list. We meet via Zoom the second Thursday of every month from 3 o'clock until about 4:30. We have a different guest speaker each month who speaks to us on a topic related to science and ideas. Two upcoming meetings on November 14th, Noah Finnegan will discuss moving mountains, slow landslides in coastal California. And,
Hmm.
and in December, Smithsonian curator Matt Schindel will speak about his new book, For the Love of Mars, A Human History of the Red Planet.
Cool.
We're always looking for new speakers. We are completely, obviously, booked for the rest of this year, but open for next year. If you know anyone personally who might speak to us, please recommend them to me along with their contact information. It always helps if I have a prior introduction from a member. So I'm looking for 12 new speakers for next year. We invite all Ashby Village members to join our group. Others interested in Ashby Village and our presentations are always welcome. Ashby Village is a 501c3 tax-exempt organization. I asked Hillary to please place a link to the Ashby Village website in the chat. And to our guests, please consider making a donation to Ashby Village or even joining our organization. We will now introduce today's speaker. I'll ask Sarah Evinger to do that. Sarah?
Hi, everybody. If you're not on mute, please mute yourself. It is my pleasure to introduce to you Veronica Tamsitt. Dr. Tamsitt has 15 years of experience in academic and industry oceanographic research. She has published extensively on marine carbon dioxide removal, the Southern Ocean circulation, and air-sea fluxes. Her research interests lie in understanding the ocean circulation and its impact on climate using a combination of modeling, ship-based, and autonomous observations. Veronica studied oceanography as an undergrad at the University of Washington before completing her PhD in 2017 at the Scripps Institution of Oceanography on the three-dimensional overturning circulation in the Southern Ocean. Currently, she is co-founder and head of oceanography at Submarine Scientific LLC, a benefit corporation, building the computational climate models it will take to make carbon drawdown possible and safe. She is also an Ashby Village volunteer.
Thank you, Sarah, for that great introduction. And yes, I am a volunteer since only about the last 6 months. Mostly I'm helping with gardening, which is unrelated to ocean science, but I'm very happy to be here today and talking to you all. Hopefully this talk will be new and somewhat interesting, and hopefully not, just the right balance of technical. And please, as Hilary said, please feel free to put questions in the chat or raise your hand if there's something you want to ask during the talk. Otherwise, there'll be plenty of time for discussion afterwards. So this is a longer version of the title that was advertised because I was requested to shorten it. But basically what I want to talk about today is ocean-based carbon dioxide removal, and the sort of question really this evokes is, could the oceans be a solution, part of the solution to climate change rather than just a victim? And this is a very new, exciting and, interesting research topic. And I'm very excited to share with you all and, hear what you all think about it as well. Okay, so I'm going to start with like a quick outline of what I'm going to talk about. First, how is the climate change impacting the oceans right now? Second, is reducing carbon emissions enough? Third, how could we remove atmospheric carbon dioxide using the oceans? What are the potential risks and benefits of this to ocean ecosystems and communities? What's the current state of research? And what are the biggest challenges to learning more and deciding if this should move forward or not? And I'm just going to get right to the answers and we'll go into all of these in more detail, but I think it's more fun to get straight to the point. So climate change is impacting the oceans now a lot. It's getting really hot. And unfortunately, reducing emissions alone is not enough, which I'll show you in more detail. How do we remove atmospheric carbon dioxide using the oceans? Basically, you can enhance natural chemical or biological processes in the ocean that allow the ocean to take up more carbon from the atmosphere. What are the risks or benefits? This has potential risks for ocean ecosystems and also potential for ocean ecosystem restoration or economic benefits. And what's the current state of this? Right now, there were a lot of lab experiments, small field trials, and model studies happening. It's a very early research phase. And the biggest challenges are how to measure it, how to get permits to do research in the ocean, the lack of a regulated carbon credit market, and public perception. And so part of that last one is to educate the community about this research and science. And so that's why I'm excited to be here. So how is climate change impacting the oceans now? We know that the oceans absorb 90% of the excess heat trapped on Earth by climate change. And this graph is just showing from the 1960s to 2020. And you can see that these three blue chunks of the bar here are all the surface and mid-depth and deep oceans. And so it's just an incredible capacity to absorb heat in that volume. The oceans also are absorbing about 1/3 of the excess carbon dioxide that has been trapped on Earth by climate change. So this is showing over time. The gray is the amount of carbon dioxide emissions, the kind of source of carbon into the Earth system. And then the sinks, like where the carbon ends up, is the negative numbers here. And it's about a split, about 1/4 or 1/3 to the ocean and land, and then the remaining in the atmosphere. So the ocean's doing a lot of work already to minimize how much heat and carbon is staying in our atmosphere. But what is the impact of this on the ocean? So of course, the most obvious one is ocean warming. And this has a lot of different impacts. It can shift habitat distributions, which can impact fisheries. It can impact a lot of other ecosystems. It can boost hurricanes, and that's very relevant this week. I'm going to show some things from Hurricane Milton from the news yesterday. And it also can directly cause coral bleaching. This is a graph of each line here in gray is a different year of the global average ocean sea surface temperature. And so you can see there's a lot of spread. The thinner black dash line here is the average from 1982 to 2010. And then the slightly longer dash line is from 1991 to 2020. So you there see, yeah, the ocean's been warming overall. It changes a lot year to year. Then if you look at the orange line here, which is 2023, about 18 months ago, like last spring, Northern Hemisphere, the ocean just went off the charts. And it has remained that way. So we are now, the red line is 2024, and we remain far outside the ocean temperatures that have ever been experienced before, in recent records. So what happens when the ocean's this warm? Basically, there's some attribution that suggests the temperatures that drove Hurricane Milton this week were made 400 to 800 times more likely by climate change. And, there's a quote here that says, "This is just horrific. The seas are just so incredibly hot, record hot, as you might imagine. You know what's driving that. I don't need to tell you. It's global warming, climate change." So this is a very current reality for many of our neighbors on the other side of the US. So what other ways does climate change impact the ocean? Ocean acidification is another one. When you dissolve, when carbon dioxide dissolves into seawater, it combines with water molecules to make what's called carbonic acid. And that essentially shifts this equilibrium in the seawater, and it reduces the amount of carbonate which is needed for anything that builds shells. So oysters, some types of plankton, corals. And it basically makes it much harder for those marine organisms to grow. The other major impact of climate change on the oceans is sea level rise. So we've observed a significant amount of sea level rise globally over the last century. And this has a lot of different impacts. It can cause coastal flooding, habitat loss, salinity change. And there's our little poop emoji appearing there. And then also erosion and deposition. And I think this one is quite remarkable when you consider how many people live by the coasts. And this map here is just showing in each country how many million people are expected that their land will be underwater by the end of the century. And this is not including the kind of increased flooding. This is just actually land that will be expected to be below sea level. So with all that, I think I've painted a very grim picture of the state of the oceans right now, but it's not all bleak. There has been a lot of progress towards addressing climate change, and the Paris Climate Agreement was signed in 2016, which involved most countries in the world making a strong commitment to reduce their carbon dioxide emissions and limit temperature increase to less than 2 degrees Celsius, and to achieve net zero carbon dioxide emissions by the middle of the century. On top of that, the Inflation Reduction Act, which was passed by the Biden administration, is the most significant climate policy ever passed in the US. Somehow, I think this fact seems to fly under the radar a little bit, and I'm not sure Biden has gotten appropriate credit for it, but it has significantly changed the trajectory of the climate and the US greenhouse gas emissions. But as you can see here, the blue was the current policy before the Inflation Reduction Act passed. And then the orange is the range of emissions scenarios now that that bill has passed. And as you can see, the Paris Agreement target is way down below that. We are still way far away from that target. And the kind of aggressive policy that would be needed to reach that target is very, very difficult to achieve. There's also a lot of other evidence that the progress happening all across different sectors isn't happening fast enough to limit warming to ideally 1.5 degrees C or 2 degrees C. And this is just one analysis that shows that the only indicator that is on track to meeting those emissions reductions target is the share of electric vehicle sales that's really exploded in the last few years. So all this gets us to the point that reducing carbon dioxide emissions is not going to be enough to keep the climate warming below 2 degrees Celsius and avoid really extreme impacts. This graph here is showing, an idealized view of what the carbon dioxide emissions should look like into the future. The red would be the gross emissions. And then in order to reach net zero, which is the goal by the middle of the century, and then eventually reach negative emissions so that we're actually starting to decrease the carbon dioxide concentration of the atmosphere. In order to do that, we actually can't do that just by reducing emissions. There are some emissions from industry, farming, etc., that would just never be possible to get to zero. And so we have to find a way to remove the carbon from the atmosphere. And that's what this green line is here. So here there's like a flat green line that is called nature-based carbon removal. And that's basically the carbon that gets removed by forest growing, like increase in forests and things like that on land that store carbon. But in addition to that, to reach net negative, we have to find ways as a society to remove additional carbon dioxide. So the Intergovernmental Panel on Climate Change, IPCC, sort of asserted in their most recent report that this carbon removal is necessary for all the emission scenarios that sort of keep us below that 2 degrees Celsius threshold. So what does it mean to remove carbon from the atmosphere? So there's 2 terms I'm going to kind of define here. One is negative emissions, which is just really anything that results in a lowering of atmospheric carbon dioxide concentration. And that can include things like changing land use. And then I'm going to define carbon dioxide removal, or CDR, and that's the process of capturing and storing carbon dioxide from the atmosphere to limit warming. And there's kind of 4 things that define carbon dioxide removal. One is that the carbon dioxide is physically removed from the atmosphere. Second, that it's stored out of the atmosphere in a way that's kind of intended to be permanent. Sometimes that's not always like really permanent, but long-term, like decades, centuries, or longer. Third is that any greenhouse gases that are generated in it, so any like energy use or other things like that that are generated while you're removing the carbon, has to be included in the balance. And then fourth, the total quantity of carbon removed and permanently stored has to be more than you emitted in doing it. And how could we do that? There are a lot of different ideas right now, and I'm sure many more ideas will be generated about how to remove carbon from the atmosphere. This kind of illustration is showing a whole lot of the existing ideas that are either being operated currently or being explored. So direct air capture is one where you literally use giant fans to suck out carbon dioxide from the air. And that's actually being deployed on quite a significant scale now. It's just quite expensive and energy intensive. And then there are a lot of other ideas being explored, both on the land, by enhancing weathering or reforestation, and biochar, which is a way you can create organic carbon and then bury it, and then a whole bunch of methods in the ocean. And I'm going to go into more detail on those. So how would we remove carbon dioxide via the oceans? One thing I wanted to point out here, there's a lot of numbers on here, so we won't focus on it too much, but this is showing, the circles here show the size of the carbon reservoir in different parts of the Earth system. And so here's the atmosphere. This is a little blue dot, 860 gigatons of carbon. And here's the ocean, the dissolved inorganic carbon in the ocean, 38,000 gigatons. So the size of that reservoir of carbon is just so enormous compared to any other. And so that means the ocean's already got a ton of carbon, but it also means it has capacity to take up a little bit, just a little bit more and make a huge difference to the whole system. And so the way we think about using the oceans to remove carbon from the atmosphere is this: step 1 is you remove carbon dioxide that's dissolved in the surface ocean water, and you create a deficit. And then through the natural kind of equilibration that happens between the air and the water, then the carbon dioxide will enter the ocean to kind of fill that gap. So what are the kind of methods being considered to or researched to explore this? So some of the ideas that have people have come up with are electrochemical ocean carbon dioxide removal, and that basically directly extracts carbon from the water. And that's a little more similar to what direct air capture does in the air. A difference being that the concentration is higher in the water, so you need less energy to extract that carbon. Another method is deep sea storage, where you take some kind of biomass, maybe wood chip, something, and try and sink it to the deep ocean where it can be stored for a long time. There's ocean alkalinity enhancement, and I'm going to explain the chemistry of this a little bit more, but essentially you're making the ocean more basic, which basically increases its capacity to absorb more CO2. Also restoring living blue carbon, so coastal ecosystems like mangrove ecosystems, seagrass, etc. They really hold a lot of carbon, and so there's a potential benefit of restoring these ecosystems and also removing additional carbon from the atmosphere. Microalgae cultivation, so that involves cultivating little algae on the surface of the ocean and then sinking the carbon that they include in their little cells to the deep ocean. Similarly, people are considering growing seaweeds or kelps, like large-scale algae, to sink to the seafloor. And then there's another idea of artificially upwelling nutrients from the deep ocean to help grow more algae and take up more carbon at the surface. Okay, so I'm going to go through a few of these a little bit more. This one, I think I kind of described a little bit. The direct ocean capture, you basically will have some kind of way to take seawater into a platform. Renewable energy can process the water and extract CO2 from it. But then you release this water that is depleted in CO2, and it will absorb extra from the atmosphere. And then in this case, you would have extracted CO2 that has to be, carbon dioxide, sorry, that has to be transported to be stored somewhere, either in rocks or in the deep ocean, or turned into some kind of permanent product. And then ocean alkalinity enhancement, I might actually just jump to this one. And please feel free to ask questions if you have questions on how this works. So the step one here is, as I mentioned before, the ocean and the atmosphere kind of try and maintain an equilibrium. So if there's more CO2 in the water than the air, it will come out. That's just like when you open your can of Coke and you leave it sitting out. That's CO2 coming out into the air. Now, when you add alkalinity, some alkaline substance, into the ocean, that makes the water more basic. So it produces hydroxide ions. And then that reacts with the CO2 in the water and creates what's called bicarbonate. And that can stay in the water stable for thousands and thousands of years. And then because you remove some CO2 from the water, there's a little more room for some from the atmosphere to come in to the ocean. And so how do you get alkalinity, increase the alkalinity of the water? There's different ways to do this. One is to do it electrochemically, is to pull seawater in. And this is, right now being done at a existing plant, like a desalination plant. And you can split out the acid and base and basically release less acidic, more alkaline water back into the ocean. or you can add mineral that's alkaline and release that into the water where it dissolves and makes the water more alkaline. Okay, what are some of the other ideas about how to do marine carbon dioxide removal? So this is ocean fertilization, and this one possibly some of you have heard of because there were experiments to do this way back in the early 2000s. And so the idea here is that there are some places in the ocean where the amount of plankton that can grow at the surface is limited by nutrients, and typically iron. And so if you add iron, then they can grow a lot more. And those little algae take up CO2, they sink to the seafloor, and that increases the carbon storage in the deep ocean. Then there's the idea of harvesting seaweeds, and this one is similar in the sense of that you could either try and sink that seaweed to the seafloor, or you could harvest it and process it and sort of create some more permanent biomass to store. And then the final method I mention here is coastal blue carbon, which I already mentioned briefly. There's been a lot of research showing how mangroves and salt marshes store quite a significant amount of carbon. And so they can kind of increase, by restoring these ecosystems, you can kind of increase how much carbon is stored in the sediment there. So I just kind of did a whirlwind through all these methods. But what I didn't really talk about are what all the risks are and benefits are, or some of that we know about. And there are a lot. And this is why this is a, I think, important thing to research really, really thoroughly and understand if any of these methods are useful as climate solutions or not, or if they're too many risks. So some of the risks for environmental impacts, ocean carbon removal could introduce harmful trace minerals into ecosystem in some cases, or it could displace existing biological production. If you, for example, are growing a new type of seaweed somewhere, you may be taking away the nutrients that would have been used anyway by some other type of algae, and then disrupting that ecosystem. There are risks, social impact risks. This could have risks to equity, environmental justice, food security, and livelihoods, depending on, how this kind of technology would be deployed. There are measurement challenges. It can be difficult to measure, report, and verify the amount of carbon that's been sequestered, and I'll talk about that a little bit more later. And then there's potentially really large energy requirements. Some of these, for example, the ocean alkalinity enhancement example, if you're going to distribute a mineral alkalinity into the ocean, you need to source that, which means mining, grinding, transporting alkaline materials, all which has a negative carbon impact and sort of cancels out the potential benefit, potentially. And what are some potential benefits? Some of these methods could reduce ocean acidification. Ocean alkalinity enhancement, for example, is basically directly reducing that acidification and restoring the ocean pH back to where it would have been before. And it's, enhancing the kind of natural weathering process that occurs. And in some cases, like the blue carbon ecosystems, that would be restoring a coastal ecosystem. Social impacts that are potentially positive, there could be co-benefits to ocean communities. If you reduce acidification, you could improve fisheries or coral reefs and any kind of industries that and community benefits that occur around that, and potential to create jobs. And then personally, I think a benefit is now by researching this, we're improving understanding of the oceans and technology to predict ocean circulation, ocean and climate impacts, which can be beneficial in a lot of other ways. So what's the current state of research? I'm going to skip over this quickly, but just wanted to show this map. This is a map of current field trials. So that's like a small scale research experiment that are currently happening on marine carbon dioxide removal. And so as you can see, there's quite a lot, but these are all very small research trials, mostly just to understand whether what works, the idea and theory works in practice, try and measure things and understand what the impacts are on ecosystems, what the benefits are, and whether there is any potential. And, this is, there's a sort of a lot of effort in the scientific community right now to kind of develop like what the kind of roadmaps are for future research. This is one example from Ocean Visions. It's a nonprofit organization. And, there is a lot of focus on researching these individual ideas for how to remove carbon from the ocean, but then also like research across the board on how to do community engagement, how to understand public opinions, how to regulate something like this. So this kind of a lot of social science research happening at the same time. And then one of the challenges to moving forward and learning more about whether marine carbon dioxide removal is a viable climate solution or not. One of the really hard parts, and that's what the part that I'm working on, is how to quantify whether the carbon was removed accurately and ensure that it's environmentally safe. And this is really hard because the ocean is a big three-dimensional moving system. And so you can't just, take one measurement and know what's going on. Collecting the ocean measurements can be really time intensive and expensive, especially when you need to go out on boats. And there are some things that are quite difficult to measure, or we don't currently have sensors or technology to measure them. So, for example, alkalinity, which is a key thing to be measured for these approaches, we don't have a sensor to measure that. So you still need to collect a bottle sample of water and take it to a lab to measure that. And in these small field trials, the kind of everything gets diluted very quickly, making it really hard to detect anything. And so I'm going to play a little video here, and this is from a computational ocean model simulation that we ran, and we did a little test of releasing alkalinity from, it says Cape Town there, but it's a Point Mendocino, basically, and seeing where that spreads. And as you can see, that purple plume here spreads very, very quickly down the west coast in the California current and gets very, very spread out. I'll just play it one more time. So it starts up here and then it spreads out. And so if you imagine trying to measure this in the ocean, it becomes impossible. And so, the way we are kind of thinking about how this might work is using computational ocean models. Like this video is from a computational ocean model, and that's built on the data. And that's a lot like how kind of weather models, prediction models work. And that can fill in the gaps. But these models require supercomputers or GPUs and experts to run them. And they don't currently represent all the relevant processes. So we're a long way from having the tools needed to quantify the carbon removed. Okay, next one. Another big challenge is permitting and regulatory. And this is just, I don't know if anyone here has ever done any kind of work in the ocean, but this is just a picture showing all the overlapping jurisdictions basically that are relevant. And so, you know, you can have territorial seas, you can have private lands, then you can have exclusive economic zones of countries, and then the open ocean. And there's all these different rules about who is responsible for making decisions about what can happen in that water. There's currently very little specific regulation for marine carbon dioxide removal. Some of these interventions kind of fall under existing regulation for ocean outfalls like desalination or wastewater. There's already really strict environmental safety requirements, and EPA is now like coming up with specific permitting rules for this type of work. And the permitting process is really slow and bespoke with an emphasis on public community engagement. And that's a really good thing. It should be that way. But I think the hard part is it's very slow, time intensive and resource intensive. So coming up with a way to make that somewhat standard and make sure that high standard is met for all kind of permits. And then the open ocean governance is complex, and international laws do impact some of this. So ocean iron fertilization with add iron to the ocean that I mentioned briefly, that's that actually there's a London Convention and London Protocol, the international treaties that actually limit the ability to do that type of intervention in the ocean. Another thing that is a big challenge is the carbon credit market. There's only kind of a voluntary market now. Some companies, big organizations like Microsoft and Google and others, like pay for carbon credits, but it's a voluntary. There's no government regulation requiring it, and there's kind of a history of low quality credits. In California in particular, there's been some revealing that the forestry credits, so credits for not cutting down trees, have been kind of low quality, and that the carbon actually stored that way is not what it seems. So without that kind of regulation, it's quite difficult. And then the other really important thing is public understanding and perception. This is really new ideas, and people quite rightly are really protective of their oceans. They want the oceans to be looked after. And so there's a sort of normal amount of skepticism about particularly adding anything extra to the ocean. And that's really understandable. So, you know, just sharing here, there's some kind of research on how people tend to have more of a positive reaction to the what's perceived as natural, like growing seaweeds, versus adding alkalinity, which in fact is a natural process that happens when rocks get ground up, but it's seen as more engineered. And that's people tend to see that more negatively. And there have been some, like, you know, noticeable community pushback to some of the trial experiments that have happened, one in the UK and one which is planned for next year off Cape Cod. So I think it's a really interesting time to be researching this and trying to understand if what the risks are, and if there's really a potential to have a positive impact for the climate and restore the oceans, and to also engage with people like yourselves in the community and educate about the oceans. So I'm going to stop there and open up for questions.
Hillary, do you want to go through the chats?
There's a couple or three questions in the chat. Veronica, do you want to just take those up, or
Sure, yeah, I can do that.
yeah, there's
And
Mark
stop
and
sharing too. Well, I raced through that in the end. Okay, I see Mark has a question. Would fossil fuel combustion and permanent CO2 storage ever reach a scale to affect the oxygen levels in the atmosphere? That's a good question. I think directly probably not. I don't know that for sure. But there's a way that they are like indirectly tied, because if you have more CO2 in the atmosphere, for many plants, particularly land-based plants, they photosynthesize more rapidly. And in that process, they're generating more oxygen. So there's ways in which, like, by changing CO2, you're changing the way that any kind of biological processes happen, and that affects oxygen as well. I don't expect that like the base concentration of oxygen in the atmosphere would change significantly, though. Does that answer the question sufficiently?
Sarah, do you want to go ahead?
Unmute yourself.
I know a lot of your research has been based in the Southern Ocean. Are all of the oceans more or less equally contaminated? And did your research start in the Southern Ocean because it was close to home, or how did that all come about for you?
No, I mean, I was at Scripps in San Diego when I started researching the Southern Ocean. I think what's compelling about it is it's like the frontier. I mean, there's so little we know about it because it's so hard to measure. And it also is unique because it's because you have basically a whole donut of ocean around Antarctica, this continuous ocean that sort of changes the circulation, and you basically have a lot of connection between the deep ocean and the surface, which means, you know, that it's sort of unusually important for taking up heat and carbon. The other part of your question is the different places that are like less contaminated, or I mean, in certain ways, yes, for sure. Like there's a lot less microplastics and nutrient pollution and things in the Southern Ocean. I mean, Antarctic Treaty means that you can't dump anything in the water down there. So it's much more pristine in that sense. But in terms of the carbon problem, because carbon dioxide mixes very quickly in the atmosphere, and the heat also, I mean, that's everywhere. There's really nowhere unaffected by that. And in fact, the polar regions are tending to feel that more strongly. The Arctic in particular, the other end, is really, really feeling it more strongly. And we're also starting to see in the Antarctic just how quickly the ice is melting because the ocean water is warming. Yeah.
So just like what I'm not clear about is, so does more carbon dioxide make things melt faster, or or is it the effect of carbon dioxide on everything, like the ozone layer and all that?
Yeah, it's indirect. So the carbon like traps extra heat in the atmosphere, right? That's the role that the carbon has. And then that heat ends up everywhere, right? And in the water, and then that melts the ice. Yeah. Let's see.
Riley has a question.
Yeah. I keep coming back when I read about these carbon capture ideas to the concept of, at least the concept I know it as, is a moral hazard. And how does it affect, in other words, if we come across some kind of an idea, some method of carbon capture that turns out to be a doable thing, has there been thought given to the reaction of the public to this so-called this solution, with regard to, you know, just emitting, just decreasing carbon emissions in the first place. In
Yeah.
other words, you know, oh, this is great. We've solved the problem. So
Yeah.
we
Yeah.
can do whatever we want to do and not worry about it. And then something happens and it all goes to heck. And all of a sudden we've got all this,
Absolutely.
you know, that,
Absolutely. I'm really glad you brought that up, and I should have talked about it at the beginning.
Yeah. Yeah.
Because it is the number one concern that people raise, and that it's a concern that I have too, that, you know, if this is done the wrong way, if the oil and gas industry sees this as an opportunity to, I
Yeah.
don't know, justify continued carbon extraction because they can just then remove it,
Right.
then it doesn't, we're never gonna, you know, that drawdown to net negative emissions, you have to get emissions all the way down and remove carbon, right? So I think that the community in research and industry that are working on this technology are just very, very much clear that this shouldn't be used to replace emissions reduction, and that this always has to be secondary, and that it, you know, should be deployed later, if at all, right? I think it's a challenging question of like how to avoid this potential
Yeah. It's
hazard.
humans.
I mean, my sense is that we are like, I think that the countries that need to lead emissions reduction are doing so. And the hope is that they will be, that if you can put the right regulatory and financial incentives in place to have this done right, and it could work. I think it's just, as a climate scientist that's been looking at this for a long time, it's sort of, you know, my reason for researching this is one, coming from, I think we have to try all kinds of things, and that we don't have time on our hands. You know, ideally we would never ever have to do carbon removal. That would be much more ideal, but we're much past the point of like having reduced CO2 enough. And then the second part for me is that you know, living here in the Bay Area, there's a lot of tech money, interest and funding, and people coming into this that don't have the right scientific background. And so to me, bringing the best available science to this is the most important thing, so that we can evaluate the risks and benefits with all the scientific information and then decide if it's worth doing or not.
Interesting.
Thank you. Joan has her hand up, and then next after that, Michael also has a question.
Recently met somebody who told me about the existence of freshwater rivers in the ocean, and especially on the West Coast, and telling me how rich they are biologically, these freshwater streams that come down from glacier melts and so on. And I'm just wondering whether you can comment on the existence of such streams under the warming trends that you described.
Mm-hmm. So I think maybe what you're referring to is like in the polar regions where there's glaciers, that there's cold water flowing out.
Partly they come all the way down to lower latitudes, and they're quite defined, that they exist as streams or rivers within the ocean.
I'm not aware.
And that's important biologically. That's what this person told me.
Okay. Yeah, I'm not aware of something that sort of, because the ocean tends to like so effectively mix, that there is like actually something that would be like a coherent stream of colder, fresher water moving south. I will say that it does get really complex, right? Because when you melt a ton of ice, that water is cold. It's also fresh. And so you kind of are changing the saltiness and the temperature of the water, which changes the density. And so some of the things I was talking about with the trends in terms of warming and sea level rise, that's like a global perspective. And actually there's a lot of regional complexity. They do,
I'll
their ice melt does have interesting impacts on the biology as well, right? Because there's often nutrients that are stored in the ice. I don't know, I'm not aware that that sort of is directly influencing things this far away, but certainly, you know, for example, if you think about in the other coast, in the Atlantic Ocean, where the Gulf Stream carries all this heat up the east coast of the US and across to Europe and makes the weather livable in Western Europe. As the Arctic changes and freshens, that has the potential to change that circulation and current, and then that, you know, so there's ways in which those local effects can have a really ultimately a big impact.
Right. Well, I was very surprised. I assumed that the glacier melt would just mix, as you said.
Yeah.
But no, this person told me no, that the water, the fresher water and cooler water persists as a well-defined stream all the way down into lower latitudes. So I guess I need to learn more about that.
Michael?
Yeah, this week Science has an article on the potential of storing wood. And I think it was a natural experiment where they found some wood in nature that had been buried for 3,000 some years. And it was still fresh and had still kept all the carbon in a stored state. How much could you actually do that if you filled the Butte copper mine with wood and put the right kind of lid on it? Does that make any impact at all?
Yeah, it's a good question. I think that, like, in theory, letting sunlight do its work to grow biomass, to grow wood or plants, and then burying that is really effective, right? Because you don't really need energy to do so, except to, I guess, chop it up and bury it. And you know, I think unfortunately the reality of like forests is that they are not really permanent stored, and so burying it is an interesting idea. I think your question was kind of like, does it scale? And that's where you really run into problems. And this is same in the ocean when you're talking about growing seaweed or something. So if you look at the land area you need to get to like a gigaton scale of carbon removal, which is what we need, you're basically starting to displace like huge amounts of agricultural land in order to grow wood to bury. And the same on the ocean. I mean, I think you would have to cover something like 10% of the global oceans, which is just a mind-bogglingly large area in order to grow enough seaweed. And then you're going to have just massive impacts on the background ecosystems. So scalability is really a massive challenge. And on land, because we use the lands for so many things, right? To grow our food, to everything. It's particularly a challenge, and I think it's what's led interest in the ocean, because there is just such a vast volume. But again, there's still questions about whether anything can scale large enough to have an impact.
Thank you. I have a question. How much do you use generative AI in your data analysis or model building?
That's a great question. We're actually writing a NSF SBIR, like a small business grant right now, to do some model development that includes like a whole part of it as using AI tools. Right now, it's, you know, AI is taking over so many things. In the kind of climate modeling world, we've seen in the weather modeling, like weather prediction, that these generative AI models are now as good or better than these conventional computational models, but much faster. And so that world is like, has changed. It's changing now. I think with the ocean and climate, there's some more difficulties. One, we don't have nearly as big training data sets because we don't have all this satellite data of the deep ocean. So we don't really know what reality is. And the second part is that when you're running for much longer timescales, with the forcing, it's harder for the AI to get that right. But I suspect that in the next 10 years, 5 to 10 years, I don't know, the technical work that I do will be all replaced by that. But we definitely use it, and I use it a lot to help me write code.
Thank you. Joan?
Yes, I have another question. We're seeing these enormous storms, and what we're told is that the volume of water in these storms is massive. It's very, very large. And it strikes me that both carbon dioxide is water soluble. And I'm wondering if these storms are the ocean, in these storms, if the ocean is self-correcting and collecting carbon dioxide and redepositing it in the ocean. Am I dreaming?
Let me just clarify. Are you suggesting that the storms, like the water containing them themselves, is absorbing extra carbon dioxide, which then I guess falls as precipitation?
If the water is it goes into the clouds distilled, not full of carbon dioxide, I assume. And but it comes down, and I was thinking that it might cleanse the atmosphere of some of its carbon dioxide in these massive storms, since there's so much water.
Right. Yeah, that's a great question. I haven't thought about this before. I think it's possible that there's, because when the water is sort of up in clouds as a vapor, that's going to change what the CO2 is doing. The one thing that's worth knowing is that with water, particularly ocean water, this depends on the temperature of the water, but the equilibration is quite slow. Like it can take months or even years for them to adjust. So on the time scale of a storm, I'm not confident whether that would have a big impact. But I think I'm sure there has been some research in what happens there and what happens to all the carbon that's like in the floodwaters, right? Once they fall as rain and that runs off. Because I'm sure that then accumulates a bunch of other stuff. So it's an interesting question, but I don't know the answer.
I would like to ask a question if I could, about skeptics. 20, 30 years ago, there were a lot of skeptics about everything you've talked about. Slowly, they've melted away. Are there any serious skeptics left who make any kind of a reasonable argument?
I mean, there were always climate deniers.
Well,
there's not as many in Congress as there used to be.
I'm talking about professionals in scientists themselves.
Oh, yeah. I mean, I think it still exists, but I think it definitely still exists and always will, right? But I think you just alluded to there's been like, my experience having started studying this field in 2008, it's really changed a lot. I really get the sense that we've sort of passed, and again, I'm in the bubble as a scientist myself, and I don't see all the perceptions, but there are some really nice, the Yale Climate Change Center does really nice surveys at the county level across everywhere in the US of climate change perception at like regular time intervals. And there's a real sense of a switch where the question of is it real or not, like man-made climate change, that's not really the question that people are debating much anymore. And, I think demographically, I've seen in my own family, older members of my family just be much more concerned about this, and the sense that it's the number of people who think it's impacting them in their lifetime is also really increased a lot too. Because I think a long time it's been the sense of, oh, climate change is going to happen or it's going to affect someone else. I think anyone who's living in the Southeast US right now is very aware that it's affecting them, and as are we here with, fire risk and things like that. So yeah, I'm not really sure how much the like professional climate skeptic, I'm sure they're still out there, but my sense is that on a large scale, at least I've seen in the US, there be a pretty a pretty big shift in the public conversation.
As a follow-up to that, are there, I recall that we had an atmospheric scientist who had just retired speak to us a year or two ago. And he worked out at Lawrence Livermore Labs. He was pretty gloom and doom about what we can really do. And is there a significant scientific community, not that argue that there's really not much we can do, and everything that you've talked about will have minor effects? Is that a serious concern among scientists, or again, am I talking about just a few scattered people?
No, I mean, I think a lot of people, I think if you're studying the impacts, or like you're running climate predictions and you see like the reality of the scale of it and the scale of migration and impact on water and food security and energy security that's going to happen, it's pretty like, kind of makes sense to be gloom and doom about it. Especially for people who've been working on it for many, many decades and haven't seen the changes. I sense in the communities I'm in, there's a lot of optimism. There's a lot more people moving away from studying the effects and just saying, look, it's bad, it's getting worse, to studying solutions, really a lot, and a lot more money going into that. And so, you know, I know we can't just invent technology to solve everything. In spite of AI, we can't. And so I believe that like that can help, but that ultimately it's going to come down to policy and economics. And the reality is that renewable energy is now cheaper than fossil fuels almost everywhere in the world. And that piece of the equation, which is not everything, but that is just going to happen by pure economics, not without really bad impacts. But you know, I think everything's moving too slow, but I'm kind of optimistic that things are moving in the right direction. It's just a matter of how to speed it up a little bit more, and how to adapt, how to be making sure that like City of Berkeley is appropriately, you know, planning for fire evacuation risk in the hills, or, you know, how to create our cities in a way that we're not so car reliant, and whatever those things are. I think that I think we've got to be just, you know, a lot of, in my mind, we focus a lot on the international and country level agreements, but a lot of this is kind of adaptation is going to depend on local communities.
Okay. Thank you. Do we have any more questions? If not, Veronica, I'd really like to thank you very much for your presentation today. Also, and bravo.
Thank you.
Also, if you ever decide to talk to us again on a related topic, you're always welcome to come speak to us. We've had people speak to us 2 and 3 times, you know, over the years about various adjunct work that they were doing. So you're always welcome to come back. So thank you very much from Ashby Village.
Thank you.
Okay. Thank you.